Okay, so today, first of all, I'm going to rather briefly discuss pseudo-coherent complexes. And I'm continuing to do this in the generality of ring spaces. So this is still section 6.1, where I discuss ring spaces and the direct categories of ring spaces. So let me just remind you that we assume that X of X any ring space. And yeah, so maybe also to notice that everywhere my definition and then other statements and proofs, I also need some integer number again. So suppose that there is such a number. So do I need to remind you the definition of an M isomorphism? So no? No? Okay, so then we'll go directly to the definition of the pseudo-coherent complex and an object. So definition will consist in 4 parts. So part 1. So take a complex F, so just the complex of all X modules. Then this F is M pseudo-coherent for shortness. I'm going to write later M PC. Just M pseudo-coherent is rather long, so just MPC for shortness. So if there is an open covering, say I of the ring space X and M isomorphisms from the EI to the F restricted to the UI, where the object EI is strictly perfect over all UI. So second part. So F, again for shortness, is pseudo-coherent, so I'm going to write just PC. So that was depending on the M, and this is just independent on the M, and the definition is the following. If it is M pseudo-coherent for any integer M,
No. You write VI.
oh yeah, that's true. So maybe yeah, more standard notation is UI.
Yeah, and so if we consider not M isomorphism, but just isomorphism, it will be perfect complex. But pseudo-coherent is not perfect.
The pseudo-coherent is definitely not perfect.
Because it's like, because we have M isomorphism, locally M isomorphism only for.
No, it's locally only M isomorphism, not the quasi-isomorphism.
Yeah, but pseudo-coherent it's M pseudo-coherent for any M. And but it's,
yeah, M is fixed. So you fix an integer and you give this definition for a fixed integer M. So I'm going to explain later what's the intuition behind this statement. So this is kind of the general thing that makes sense on any ring space. If you restrict your attention to schemes, you can say more precise things. If you restrict your attention to Noetherian schemes, you can be quite precise what this is in elementary terms. That doesn't require to know what pseudo-coherent is. But let's postpone these discussions later when I finish the definition and several more remarks. Okay, so 3. Now, so before it was definition for a complex. Now in 3 I just give a definition for an object in the direct category. So I take an object in the direct category of the OX modules, and I say that this object is M pseudo-coherent if is isomorphic in the derived category to an M pseudo-coherent complex. So essentially the same definition as we used for the perfect objects. Yeah, and also maybe also the part 3 fixed notation. So again, the notation is not standard, this is my notation, but it is convenient when you formulate statements and prove something just for shortness of the notation. I'm going to write P Koch. Potentially that depends on the M, and this M can be omitted, then I'm just talking about the pseudo-coherent that is for any M. So on the pseudo-coherent of the OX modules, this is the full subcategory. Full subcategory of the derived category of OX modules of M pseudo-coherent objects. Okay. So I put this M here in the notation and in the explanation in parentheses, meaning that I can omit this. So I can write this P Koch just of OX without M, and this will be pseudo-coherent. And I can also add N back, and this is will be fully fixed M. And finally,
It's also triangulated here.
it is triangulated, but it doesn't follow immediately from the definition. It's actually not just triangulated, it's actually thick. Okay. So finally, I take F to be just a module, also just an OX module. So this is M pseudo-coherent if, well, let me write for shortness like this. I just consider F, put this into degree 0, and just look at this complex. So if this is M pseudo-coherent, using this notation, you can avoid writing words. So that's the definition. Maybe at the moment not clear why this is an interesting object, but this is kind of classical definition. It goes back to the SGA6. Now, several remarks about this definition. So first of all, you can clearly notice that if X is quasi-compact, and we're going to work mostly with quasi-compact schemes, for shortness for later on I will just write QC. So quasi-compact morphism, quasi-compact scheme. So this is, so if X is quasi-compact, then well, you can clearly see that pseudo-coherent for any M is a subcategory inside the D minus of OX. So, second remark.
Why is it so?
Well, you just look at the definition, kind of. From the definition, you can see that locally, you look here, locally, so if you just kind of embed the definition of M-isomorphism here, this is bounded above.
M-isomorphism, it's when to the left, it's isomorphism, yeah?
No, M-isomorphism means that you can take this map, you can take the cone, you will look at the cohomology, and all the cohomology are trivial to the right of the M.
Ah, okay. Ah, yeah. Mm-hmm.
So that's a simple remark. So the second is not so simple, but I still want to leave this as an exercise. So F is pseudo-coherent on the M pseudo-coherent if and only if there is an open covering, let's say again called UI of the X, and with this open covering M isomorphisms from UI to the F restricted to the ui in the derived category of all ui modules. So with condition that the EI are all strictly perfect. So 3. Immediately from the definition, you see the following. If you take pseudo-coherent for the M, then this is kind of subcategory or subclass in the pseudo-coherent with the index n. And that is for any n which is greater than m, greater or equal than m, of course.
And it's also full subcategory, yeah.
What?
Peak of m in peak of n.
Oh yeah, by the definition, yes. So you can see from this definition, when you look at the definition, well, from this remark, you can see that from the in the definition, the most interesting case is you can try to take this m as negative as possible. And finally, remark number 4, again quite trivial from the definition. If you have f which is m pseudo-coherent, and then you can take the shift, say f shifted by some I, then this is again pseudo-coherent, but clearly with the shifted index, so m minus I. Again, this just follows from the definition and m isomorphism. Okay, for the next statement, I need the following lemma, which I think is kind of useful anyway, and also very simple. So let E be a bounded above complex of direct summons of finite free OX modules. Finite free OX modules. Or if you have a scheme, then of course this will be bounded above complex of vector bundles. So then,
So bounded above is perfect. It's just as perfect, isn't it?
no, perfect is bounded above and below.
Ah, so it's
So perfect is kind of locally just a finite complex of vector bundles. So then E, yeah, so maybe still I'm explaining this with the perfect. So the idea for the perfect that this is bounded complex of the vector bundles, and idea of the pseudo-coherent, if you kind of have a nice scheme, for example, an Arthurian scheme, then this will be kind of the complex of vector bundles bounded above.
what is this called?
Well, it's kind of a theorem for Arthurian schemes.
Isn't it? It's like locally it's isomorphic to something finite.
No,
Homology finite.
no, because this is only M
Oh,
isomorphism.
it's yeah. Mm-hmm. It makes sense.
Yeah, but I'm going to return to this later anyway, so let me finish the statement of the lemma. So then E is homotopy equivalent to a bounded above complex of finite free OX modules. Bounded above complex of finite free OX modules. So you kind of up to homotopy equivalence, you can remove this direct summand of a finite free OX module. Just say this is finite free OX module. That's the statement. Okay. So let's show this. So since this is bounded above, let me fix this kind of the index. So I'm going to assume that I have index, which is just an integer number. So such that if I take EP then this is 0 for any p which is greater than n, and this en, so this component is not equal to 0. Okay, so then we can choose, so we can complement and write f with the index n as the en plus gn, right? So this is for the n. By the definition, such complement gn exists, such that fn, so fn is finite free OX module. Maybe just let me write this as a formula for shortness. Okay. So this is for the n, and then I use the induction to go from the n to the n minus 1, etc. So let me say that the for p which is less than n, I've set by induction this is the key step. I'm saying that the f with the index p, this is, well, ep, which is given to me, right? So then I already know by the induction hypothesis that I kindly constructed the complement g with the index p plus 1. So I add also g with the index p plus 1, right? So from the previous step. And then still this I again kind of by construction, these are summands of a finite free OX module. I can also find another complement GP such that this direct sum is again, so this is a finite free OX module.
У нас индукция почему?
По номеру P, то есть я построил, и я после этого уже P минус 1 я называю и так далее. Ну, соответственно, я перехожу от P плюс 1 к P.
Это наглядно как построить.
Вот.
Ну, для у нас просто мы знаем то, что EP, EN это директ соманд. Значит, у него есть P будет дополнительный.
Да.
Вот мы уверены.
Вот это же P плюс 1, это тоже P, которое для FP плюс 1, или это разное?
Да. So, well, for example, well, if you kind of do this for the, say, e is equal to the n minus 1, right? So then you have this g to the n, which you constructed here on the previous step. And then you add the summand, and then you use the summand on the next step. Okay. So the differential on the f. So I also need to define the differential. So the differential on the complex f is sum of this kind of f. Each fp has 3 components, so this is the sum of the 3 maps. So sum of the differential from which you get on the e. Oh, don't give a name to this differential, just explain this in words. So on the component, you just, on the first component e, you just apply the differential in the complex e. So then on the second component, you use the identity map. That's from the GP plus 1 to the GP plus 1. And on the last component, this is 0. And 0 on GP. You can imagine you have corresponding matrix, you can take the square of this matrix and you see the square is 0. So that's really a differential. Okay, now, so I constructed this f, and I also have 2 maps, the simplest possible maps that you can think of. Let me call this pi, so in the index p. So this is from the EP plus GP plus 1 plus GP to the EP. That's just the projection. Forget the components, second and third component, and just take projection to the EP. And there's a map in the other direction, the inclusion of the first component, so I with the index P. We'll just take the inclusion of the first element. And it's very easy to verify that actually this is a two maps on the complexes. So let me make this simple verification to you. So I and I are maps of complexes, right? And also, well, so of course this complex M that I'm constructing is the complex which is homotopy equivalent, and this complex of finite POX modules. So these maps are supposed to be the homotopy equivalences. And in one direction, if you just look at the composition of the pi and I, so you include and then project this clearly identity. So in one direction, this is very simple. And what we need to show, so what's left, is that we want to show that the say identity minus the composition in the other order, so I and then pi. So this is no homotopic. No homotopic. If we can do this, then we are done. Well, it's kind of very straightforward computation. Oh, this is this map. So I start with the P. So this is from the complex F back to the complex F. So this kind of endomorphism of the F. And I want to show that there is a homotopy, and I can just explicitly write this homotopy. So let me just write 3 terms and then another 3 terms and then the formula for the homotopy. So, and when you kind of write this formula for the homotopy, you see the reason why we kind of construct this Fp as the sum of 3 terms, P plus 2. So I'm just writing what's Fp minus 1, Fp, and Fp plus 1 are.
Then you mistaken. It's the
Yeah.
second term.
This is P plus 1. So then I just repeat the same thing one more time. So I'm claiming that there are, so here I have this map identity minus composition of the I and pi. So I claim that there are homotopies, which I'm going to call HP and HP plus 1. Right? And then, well, this is the abelian category. You can use the phrase Mitchell embedding and work with the elements, but you can also, I'm going to kind of give the formulas for this HP in terms of the elements, but you can also kind of work out what the definition is in terms of the, well, you can define like this as sum of some maps. So, but in terms of formulas, it's very easy to see that this works. So if I have E, X, and Y, so this is a kind of triple of the elements of this direct sum. So then, I, by definition, say, of course, that there is no freedom to give you any other definition. I just take the last component and send this last component by the identity map to the middle component. So, of course, the same, so this has to be HP with the upper index. So, for HP plus 1, of course, the definition is the same. It's kind of very elementary homological algebra here. just for completeness, I'm repeating the formula. Later it will be a little bit easier to check the computations. Okay, so then to check that this is a homotopy, well, I first can compute the differential, say with the index p minus 1 and the hp plus the h a, using the low index hp plus 1 dp, right? So let's take this kind of supercommutator and compute the supercommutator on the e, x, and y. Well, what happens if you just take this triple and apply the first map?
0.
No.
Why? You take the middle part, and the middle part, oh, it's GPA plus 1. It's just go to the, it will be just 0, 0, 1.
No.
0, y 0.
Yeah. No, no.
Why?
0, 0, y, I think.
Yeah. What?
Almost correct, yes.
P minus 1.
And if you do this for the second part, well, by the same reasoning, you'll get 0, x, 0. Right? Just an explicit computation. And then you can do again a simple computation with the ID minus composition of the I and pi. Apply to the E, X, and Y. And of course, if you apply the ID, you just get E, X, and Y. And if you apply this composition of the pi and I, you'll get E,
0,
0, 0. So as you can see, this is the same as this thing. So indeed, we have the formula for the homotopy. So H is a homotopy to the, well, showing that this map is homotopic to 0, or in other words, IP is homotopic to the identity. So that's the end of the proof.
Can you please explain again why FP is a free OX module?
Hmm?
Why FP is a free OX module?
Well, because when I look at this definition, and this is given and this is given by the previous step, but these two modules are summands of a finite free OX module, right? So if they are summands, then the sum is also a summand.
Okay.
So there is a complement GP.
Mhm.
Okay, so proposition, which starting to show how we're supposed to think about pseudo-coherent at least modules. So let F be OX module. I also fix some non-negative integer R. So then F is pseudo-coherent with the index minus R if and only if. So this is a local property, so locally on X there is an exact sequence of OX modules of the following form. So I have E, write that like the part of the free resolution E with the index minus R, then this index is increasing until I reach E with the index 0. And this is mapped to the F, and then this is 0. So
And from the left, it's not an inclusion.
here? No. No. So where this, all these terms that you see in this sequence, EI, these are finite free OX modules.
So it's resolved.
So you can see that at least when you don't have a complex but just a module, this is a very straightforward kind of interpretation of the minus R pseudo-coherence. It's just you're saying that you have this resolution locally by finite 3 X modules. So this is kind of the generalization. For example, if you have the R is equal to 0, right? This kind of means that locally this is a module of finite type.
What is model of
Finite type.
Mm.
So a quotient of the OX,
Mhm.
there's some finite number. So if you have this for the R equal to the 1, it means that F is locally a finite presentation.
Mhm.
And then there's kind of this generalization for any index R. Okay. So let's prove this. So, in one direction. So I'm going to assume that the F is minus R pseudo-coherent. So since this is a local statement, so since this statement is local on X, without loss of generality, I'm going to assume that I have some E, which is strictly perfect OX module, and I have a minus R isomorphism from the E to the F. Right? So this is what I have if I just plug in this statement the definition of the pseudo-coherent with this index. So then I claim, and I'm going to prove this, so we can take E such that the component EP is equal to 0 for any positive P. So indeed, so let M be the maximum, N will be the maximum such that En is not equal to 0, and assume that this n that I defined as a maximum is positive. Okay. So then we have we can look at the cohomology of the with the index n of the complex E. So what are the cohomology here?
In model isomorphic to homology of F. Which
Yeah, so it's isomorphic to homology of F, but F is just the module. So by definition, there's only homology at 0.
Why F is just a module?
I assume this.
Ah, yeah, that's true. Ah.
So since F is just a module, and this is an M isomorphism, or actually minus R isomorphism, and R is non-negative, so here we look at the some positive homologies 0. Right, so for positive M. So since this is the cohomology is 0, we can claim that the map from the En minus 1 to the En is an epimorphism. So locally on the X, I kind of can split this epimorphism. I can write En minus 1 as the E prime plus En. So, and then the recipe is to replace E, which we already have, by a new complex where I have all the terms as before, and I only modify the two terms. So here, instead of the en minus 1, I'm going to write e prime, and after this, I'm going to write 0. Right? So this is kind of one step in the induction, then you just do this induction on the n, and you get the result, right? So and use the induction. So by this inductive argument, you can assume that this is indeed true. So we can take this E such that EP is 0 for the positive group. Okay. So then we're almost done. We just need to kind of realize that when we have this, we just can say that if I take the truncation and the good truncation at the level minus r plus 1 on the left, so of the object E, right? So then, well, first of all, you can notice kind of this is I'm just explaining, kind of remind you what's how this truncation works. So this will be the complex which has co-kernel of the differential with the index minus r. So then all the other terms are just the, I need to write one more term. So here there will be e minus r plus 2, and the last one is of course e0. So there's this truncation, and this truncation is still mapped to the f, and this is exact. So this is an exact sequence. So finally, you can also look at another exact sequence, which is very short. So E with the index minus R, then the differential maps this to the E with the index minus R plus 1. Then I take the co-kernel
What's exact?
of the differential. Well, because you have this minus R isomorphism,
Yes.
right?
And that means that for anything that yeah. That's true.
Yeah, so this follows because you have minus R isomorphism, so this observation is kind of a trivial one, right? This is more just a definition of the co-kernel. And then you can see that you can take this exact sequence and kind of spice them together. So this short exact sequence with 3 terms, you take co-kernel, map it here, right? So this is the same as this. And then you get the sequence with just additional 2 terms, which is again exact, right? And that's what we need, right? We proved that we have a resolution of this kind. Okay. Not a resolution, but an exact sequence of this kind. Yeah, so we need to say one more thing. So since this was yeah, so the claim is that the EI that they have in the statement are finite free OX modules, right? And this E, right, this is only strictly perfect. So the terms at the moment, terms here that I constructed are direct summons of a finite free modules. So to finish this proof, I need to say that we use the previous lemma. So by the previous lemma, we get the result. Okay? Because in the statement, in the proposition, I'm claiming that these are finite free, and here, when I use the definition of the pseudo-coherent, I only know that this E is strictly perfect, so the terms EI are only direct sums over finite free OX modules. So, and the lemma saves the situation.
Does we assume here that F is an object of derived category?
F is just an OX module.
Yes, but when we speak about pseudo-coherence, does we assume that F lies in derived category and
Yeah, so this is part of the definition with number 4.
so we have only quasi-isomorphism with some minus or perfect OX module.
Yeah.
Я имею в виду, что вот у нас F объект производной категории, и у нас есть какой-то квазиизоморфизм изоморфизм в производной категории. Но там же домик такой, не обязательно же он является морфизмом настоящим. А тут как будто взяли, что вот это эпсилон и F, между ними сразу минус F.
Ну, вообще я не понимаю, почему вы говорите, что F из производной категории. Мы же договорились, что из производной категории это то, что квазиизоморфно псевдокогерентному. Ну, F мы тут просто написали, что он псевдокогерентный, и все. То есть просто псевдокогерентный. Это да. У меня вопрос. Николай.
Yeah, I think you have a good question. So in the proof, I'm assuming that I can work with this isomer. So this is no. I think what saves the situation is that I work locally, right?
Yes.
And locally, I can say that this is just a map of the complexes. Right.
Почему?
We had this lemma on the last lecture, I suppose.
Well, this is by definition, right? Because the definition has 4 parts, and the first part, in the first part, the claim is that I kind of locally I work with complexes, right? It was definition for a complex, and locally there is an M-isomorphism for the complexes.
Mm-hmm. Yeah, but it's M-isomorphism for complexes, but F is quasi-isomorphic to some complex that M-isomorphic to yeah.
So that I don't think that this is a problem. So why that's a problem? So
Yes.
I can work locally. I have one complex, I have another complex, and just minus R isomorphism of these complexes.
Yes. Mm-hmm.
Is it true that any map from derived category from strictly perfect complex is just a map of complexes?
Well, not exactly, but we proved
It was
this kind of technical lemmas L1, L2, and L3. So the conclusion of L3, if all the technical and the assumptions are satisfied, then this is true.
And
This solves this problem, right?
No, I think you don't need to involve this technical lemma because, again, I'm saying just I can work locally. And locally, by the definition, this R isomorphism is R isomorphism, which is just a map of complexes. So I think that's the explanation.
so yeah, for F there is some F quasi-isomorphic to some perfectly coherent complex.
Strictly correct. So,
Perfectly coherent complex. Perfectly coherent minus R complex.
but this is
And
what
we just compose it with this quasi-isomorphism, yeah? So like F is the complex of derived category. It's perfectly, minus R perfectly pseudo-coherent if it's quasi-isomorphic to some minus R pseudo-coherent complex.
yes, yeah. In this sense, yes.
Okay, and if we can, yeah. I hope you all understand.
Можно еще вот глупый вопрос? Когда лемму доказывали, у нас там длина комплексная единичка увеличивалась.
Почему да?
Нет?
Нет. Он как бы был ограничен там где-то, где было n, да? Вот, и было и n, после этого были нули. и в fn то же самое на позиции n там что-то, дальше нули.
А вот в FP входил же комплекс 1.
Да.
И тогда у нас, если мы здесь построили комплекс, то самый левый член это минус R.
Well, I write it here, but then erase this. So if you have something like, say, you have en, and then after this, you just zeros everywhere, right? So then there is this fn, which is just en plus gn, right? There are maps here. So then on the next step, you have en minus 1, and then the term here will be the e to the index n minus 1 plus the g that I constructed on the previous step, so it's plus the gn, and plus you complement g with the index n minus 1. So that's the construction from the lemma. So there are maps. This is the differential. There are projections and inclusions, but you can see that it's exactly in the same degrees.
Yes, but on the left we will have also.
It's infinite to the left. It's bounded only on the one side.
Yes, but we want to. Okay, we don't have 0 in the left, so there's no such problem. Okay.
So I'm going to erase this. So I want to say that if you want to prove in the other direction, then this is actually clear, right? Because, well, let me say that this sequence that I have of this statement is star, right? So then the star, which is given to me, is actually is minus R isomorphism. Right? Just look at this as the map of the complexes, look at the corresponding cone, and look at the cohomology. All the cohomology are trivial at the right positions. So that's minus R isomorphism, and there is nothing really to prove in this direction. Okay. So I have several more propositions which are kind of relatively easy to show, so maybe I'm going to leave several statements as an exercises. So for example, the next one. So let m be an integer, and suppose we have a distinguished triangle. Some distinguished triangle in the derived category of all x modules. So then the claim is that if the two terms in these triangles, if E and G are pseudo-coherent with the index m, so then, kind of by looking at looking at the definition more or less, we take this distinguished triangle, take the definition of pseudo-coherence, and you can conclude that the middle term f is also m pseudo-coherent. And you can formulate two more statements of this kind if you do the rotation. So you can assume pseudo-coherence of these two terms, then you can conclude the pseudo-coherence of the E, but you need to write the correct index. So I'm going to leave this as an exercise. So in this exercise, actually, this technical lemma L2 will be useful. Because you kind of what you do, you just, right, so you have, for example, these two terms, you can write the corresponding m isomorphism here, m isomorphism here, maybe rotate so that you get an isomorphism here and here, and then you can write a map here, which will be a map of complexes and take the completion. So to say that this will be a map of complexes, not just a map in the direct category, you need L2. So, well, check the, I think the proof is straightforward, you can use it as an exercise. So another proposition about the pseudo-coherence is the following. So suppose I have K and L are two objects in the derived category of OX modules. I assume that I have some integer M. So then K and L are pseudo-coherent with index M. M pseudo-coherent if and only if the direct sum is M pseudo-coherent. So kind of the statement is that the pseudo-coherence is closed under direct summas. So in one direction, if you assume that K and L are pseudo-coherent, well, you can more or less just use the previous proposition, right? And you just look at the splitting distinguished triangle and use previous proposition. So that's the trivial direction. So in that direction, you need to do something. So again, all the statements are more or less proved by saying we work locally. So working locally, we may assume that the direct sum and hence direct summons, so K L are bounded above. So we know that the K plus L is bounded above, hence every direct sum is K and L also bounded above. So then we can say that if I look at the, say, L, so I can do the proof for the K, I can do the proof for the L. This is symmetric situation, so it's enough to show for the L. I take a shift by some M, and I assume that this is pseudo-coherent with the index M for any n which is sufficiently large.
What we can assume? Why we can assume it?
Well, because this is bounded above.
And what?
Well, if you kind of move this by very high number, well, by very large number n to the left, right? So then you look at the definition of the pseudo-coherent for some m, and this is satisfied by trivial reasons.
L is some why? I don't understand.
Oh, because M pseudo-coherence is kind of some condition on the cohomology starting from the M and to the right. Right?
Yes.
And you move it it's in that way that there are no cohomology starting from the M to the right. Okay, so then again I can look at the two trivial distinguished triangles, so K, which is mapped by the identity, and then 0. And I take the sum with another splitting distinguished triangle where I have L, L, and then the direct sum with a shift. Right, so I have the sum of these two distinguished triangles. Right, and from this, since I know that L plus K is M pseudo-coherent, right, I can conclude by looking at the direct distinguished triangle, which is the sum, I can conclude that the L plus L shifted by 1 is pseudo-coherent on the x. Okay. So then I can take this object, this direct sum, and
How do you say this?
by that proposition that I left as an exercise. Right, so we have a distinguished triangle. This term is M pseudo-coherent, this term is M pseudo-coherent, hence
We
this.
don't know this, we want to prove it. Ah, it's K plus L. Ah, yeah,
Yeah.
of course.
The sum is pseudo-coherent. I want to show that the sum and L is pseudo-coherent.
Yes.
So in the proposition we have that the extension of two coherent sheaves with respect to m is also such, but here
Well, in the proposition, you can also take the proposition and rotate the distinguished triangle and use the statement for the rotated distinguished triangle.
but the k plus l on the right from l plus l1 lies in pseudo-coherent n plus 1.
Yeah, I suppose it should be not M. So,
Yeah, I think that's right. Yeah. Yeah, let's see. Will this be really a problem? So that's pseudo-coherent in the n plus 1. But anyway, what I want to do next, I want to shift this by some little n and look at the L shifted by the little n plus L shifted by the little n plus 1. Right, so this is pseudo-coherent, well, for the m plus 1 minus n, right? Which is, of course, is contained in the pseudo-coherent with the index m, right? Okay, so and then I look at the distinguished triangle where I have L with a shift n plus 1, and this is a direct sum until the L shifted by n plus L shifted by n plus 1.
this works only if n larger than 0.
Yeah, n larger than 0. So L. Right, so we have this again split in distinguished triangle, and we know that if I have the shift which is sufficiently large, I have M pseudo-coherence. And this allows me to do kind of the induction. Right, so by induction, I can say that the L shifted by N is pseudo-coherent with the M, and this is for any n which is positive.
Yes. But not for L.
Yeah.
So it kind of breaks.
Yeah, that's a problem. That's a problem, and I don't see how I can fix this, because I only have this triangle, right? I can't really write something else. Can we fix this? Okay, so is that really true? Well, Wait, maybe there's no problem. So in this, so here in the proposition, do we agree that I can say the following? If I take E, which is pseudo-coherent with the index m plus 1, I'm going to write for shortness OX, and I also take the second term of the distinguished triangle to be just pseudo-coherent with the m, right? Then by the shift argument, I think what we can show is that the G is pseudo-coherent with m. I think that's correct.
Правда, что когда мы сдвигаем пучок на И, то показатель псевдокогерентности уменьшается.
Да, да.
Да, и поэтому...
Ну да, тогда мы подкручиваем,
То есть
как получается что-то ближайшее
Да.
псевдокохерент m, посередине G, а потом что-то ближайшее псевдокохерент m. Ну да. Ну вроде да. Ну да, и тогда здесь все-таки псевдокохерент m.
То есть он, да,
Yeah, so yeah, that's exactly my idea how we can fix this. So then I can write m here, not just m plus 1. So then there will be m minus n, and then the n is any numbers which is non-negative. Oh, yeah, it's okay. So that's the proof of this thing. Okay, so next proposition, which I think, again, I can leave this as an exercise because this is kind of just straightforward using of the definition. So let F be a map of ring spaces so it's a map of ring spaces. I have some integer m as usual. So then I claim that you can take the derived pullback, and the derived pullback preserves the property of being m pseudo-coherent. So let me get right that the proof is exercise. But I think again this is a straightforward exercise. So what you need in the proof, again, you would say that you work locally, then you replace some object by isomorphism by strictly perfect object, right? And strictly perfect objects by the LF upper star map to strictly perfect. So you only need to kind of take the distinguished triangle with an M isomorphism, kind of apply the factor, and check again that the cohomology for the cone the correct one. So think about the details. Okay, so let's prove the following lemma. So let E be locally bounded above complex of X modules. And I assume that all the terms, so EI, are pseudo-coherent without index. Pseudo-coherent for any M. So and this is of course for any I. So then I want to conclude that the E is pseudo-coherent OX object. OX complex. Okay, again, working locally. So we may assume that E is bounded above. Okay, And then there is an elementary observation that probably I haven't used so far, but I'm going to use this several times again. So that you can say that the complex is pseudo-coherent with the, well, M pseudo-coherent for some M. This is equivalent that you can take the silly truncation from the left at the level M minus 1, and this is again pseudo-coherent, right, which follows from the definition and fact that they have isomorphism. So you can only check this property of being M pseudo-coherent if you kind of look at the part of this E that kind of lives only in the degrees starting with M minus 1. Okay, so, and this kind of saves the situation, right? Because instead of working with just a complex which is bounded above, I can work with a complex which is just bounded. And then, since I know this property for each term in the complex, I can use the induction on the lens in the following distinguished triangle. So I look at the silly truncation at the level I plus 1. Then this is silly truncation at the level I. And then the quotient is the EI, which lives at the degree I. So then EI with the shift minus I, oh, this is still pseudo-coherent module, and by induction on length, the E is pseudo-coherent. Well, kind of this is, maybe first I say this is M pseudo-coherent, but this proofs works for any M. So the conclusion that this is just pseudo-coherent for any index.
Is it true that good truncation will be perfect?
Good truncation will be perfect? No. Well, because in the good truncation you get this co-kernel, and for the co-kernel you can say that this is kind of vector module. So I kind of need some additional assumptions that give you that this co-kernel is also locally free. Yeah, so I think this is a simple lemma, but it kind of explains something, right? So we can think about the pseudo, well, by this kind of procedure with this induction of the lens and kind of this doing, we can naively think that, well, a pseudo-coherent complex is something where complexes with pseudo-coherent terms. No, I didn't prove this from that, and it's not true in general. But you can prove some statements, for example, for Noetherian schemes. Maybe I kind of formulate this maybe as an exercise, because I don't have time to do this on the lectures. But you can show that, for example, if X is Noetherian scheme, then say some E is pseudo-coherent, M pseudo-coherent on the X. Well, this means the following, that you have the position, well, in this E you have the position M, right? So you have also some position, say large N, and after this position you get zeros, right? So you kind of have this kind of three regions. You have something in the middle which is finite, you have something on the right which is infinite but zero. So the claim is that here, if you take the cohomology, so take cohomology I of the E, and this is coherent OX module. Right, so in this kind of bounded region, this is coherent. This is, of course, for any I, which is in the region M and N. Right, so M pseudocoherence is just the coherence of the cohomology in the region between M and N. So if you kind of want to forget this M, right, and say that this is M pseudocoherent for any M, so kind of go to the minus infinity. As I say, in the definition of pseudocoherence, you want to take this M as negative as possible. It's the most interesting case, right? So then you can say that on a Noetherian scheme, right? So then
And this works for any ring space, yeah?
no, this is for Noetherian scheme.
Why?
Well, because I don't do a proof, I'm just claiming the result. For example, here I have the notion of the coherent module, which makes sense only for a scheme.
Yeah, but for any scheme it works, isn't it? What you need from Noetherian? Quasi-compactness? Isn't it?
Well, I
For
definitely
coherence, you need quasi-compactness, kind of.
for coherence. No,
Well,
for coherence, I don't need quasi-compactness.
Okay. There is always problems when you define coherence not on Noetherian scheme.
Why there is a problem?
Then two definitions of coherence don't match on Noetherian scheme.
No, which two definitions?
Definitions as finite representation of locally finite representation of finite fluid, and
That's the correct definition, yes.
and definition of as locally it's isomorphic to
That's a stupid definition, you can ignore this.
Okay, if you set up like that, then yeah, we don't know.
Yeah, so I want to, well, yeah, maybe, I'm not sure, so maybe this is true not for Noetherian scheme but quasi-compact, but for what I want to say now, this is definitely something that requires Noetherian scheme. I want to say that when you look just at the pseudo-coherent objects, right, on a Noetherian scheme, then you can identify this with the D minus with coherent cohomology. Right. So, well, you can.
Equal?
Hmm?
It's equal to this.
This is just the same two full subcategories. So you can see that kind of in the Noetherian situation, there is no reason to introduce this pseudo-coherence, right? Because it coincides with something more elementary. But the point is that this duality theory is actually work in the greater generality. It works for the quasi-coherent, quasi-separated morphisms and quasi-coherent, quasi-separated morphisms and schemes. So you don't need to assume that the scheme is Noetherian. And for some statements, kind of the right generality is the generality when you work with the pseudo-coherent complexes. So this is why I decided to include this. So there is one more proposition, which is kind of more or less standard, and we've done these things a couple of times. So maybe I can just formulate this as an exercise. So proposition. So let A be an abelian category. I have two triangulated functors from the derived category of the OX modules to the derived category of this abelian category. So these are triangulated functors. So this is the finite sign. And there is eta, a trinatural transformation from the phi to the psi. So this is trinatural transformation. And I suppose two things. So suppose, well, first, that the component of this trinatural transformation for the object OX structure shift, this is an isomorphism. And the second assumption is that there is some integer large M such that these functors phi and psi map the derived category where I have cohomology only up to index I, so this is the standard notation, right? But I don't think that I introduced this before, but I think it's evident from the kind of notation what it is. So there is no cohomology. So all the cohomology are concentrated up to the index I. So then this is mapped to the derived category. Again, cohomology now are concentrated at the I plus N.
Finite amplitude. It's,
The functors,
yes, factors of finite amplitude, isn't it?
I'm not sure about the terminology. Maybe they're called something called bounded on the right also.
Yeah.
Yeah, so this is,
Oh, we have a finite amplitude if it's like there's only finite cohomologies and it goes to finite cohomologies to bounded. Yes, it should be something like bounded above.
so then the conclusion is that this eta component with some object f is an isomorphism, for any object f such that there is M isomorphism from the E to the F, and E is strictly perfect on X. Yeah. So I'm going to leave this proof as an exercise. Okay, so maybe it's time for a break. It's time for a break.
У нас была такая же аналогичная теорема на X изоморфизм, и выраженные функторы, там, ну, если мы берем какую-то прямую сумму нескольких у X, то понятно, почему это изоморфизм. Ну, потому что у нас там есть вот такой треугольник, ну, там у X, здесь у X плюс 2. Понятно, почему, если здесь изоморфизм, то здесь тоже будет изоморфизм. Вот, а если у нас у X, он как-то раскладывается на у X1 плюс у X2. То есть, почему? Если у нас X не говорит простого. Если какая-то из двух кусочков состоит. То есть если у X есть соматы, то это правда. То есть как это
Вы спрашиваете,
почему они будут изоморфизм? Почему фи от X? Ну, почему тета от X1 будет изоморфизмом? Да, я не совсем понимаю. Кажется, что он какой-то видимый треугольник,
мне кажется, что это очевидно, как будто бы.
Ну да, то есть это типа спрашивается, что то, где тета изоморфизм, это типа категория. Да. Это вот как-то очевидно.
Какие там предположения, просто что это было
Вроде вот это все. Да. Ну, вот это у X изоморфизм.
Ну, здесь было. Сейчас. А, это же написано, что это было.
Ну да, это осталось упражнение.
То есть, если написано, что это упражнение, значит, когда я это придумал, мне казалось, что это очевидно, может быть, что-то пропустил. То есть здесь как бы да, логика такая, что хорошо, мы рассматриваем категорию, какую-то категорию, для которой это, соответственно, если мы берем объект из категории, то на этой компоненте это изоморфизм. Задается вопрос, почему это категория? Это важный вопрос, это вообще ничего не получится.
Ну, в принципе, он как бы и все решает более-менее.
Да, я говорю, что если мы это понимаем, то мы все остальное тоже понимаем. Почему это... Ну да, начинает, конечно, очевидно, как у нас есть треугольник, здесь подобьет, еще подобьет, у нас есть изоморфизм посередине. Причем спрашивается, почему это будет изоморфизм на двух классах. Казалось бы.
У нас бывает такое, что у нас два объекта как бы не изоморфны, то есть, там, А не изоморфен на штрих, Б не изоморфен на Б штрих, но А плюс Б изоморфен на А штрих плюс Б штрих. Тогда да, тогда вообще непонятно, что это может быть. То есть вот теорема, да, там какой-нибудь неприводимый приведенные схемы понятно, более-менее. Ну там потому что ОХ как бы никак не раскладывается, и прямая сумма иксов тоже вроде никак не раскладывается, кроме как прямую сумму иксов. Вот. А вот если у нас...
Сейчас здесь предыдущий режим, который был наказан до этого, то, что строго совершенные образуют толстую категорию.
Да.
И у меня написано, что следствие функции надо их использовать.
Не то, что они образуют толстую, а то, что они вкладывают.
Ну да, то, что они находятся.
Нет, да, это надо как-то использовать. Это используется так, что если мы знаем, если мы докажем это для фиг по x, то это очевидно для s perfect. Вот, вопрос как раз касается для фиг по x.
В том упражнении, где происходит склейка из морфизма в производной категории в один большой морфизм, есть где-то его решение в каком-нибудь тоже книге или статье?
Да, есть. Вот это, пока я сейчас все рассказываю, я следую этой книжке Бетхорна и Герца, которую я в начале курса рекомендовал.
Вот про алгебраическую геометрию.
Да.
И там написано решение, или оно тоже как упражнение дано?
Но это я скоро не помню, но мне кажется, скорее всего, решение есть. Ну, может быть, такое коротенькое, но оно там должно быть.
А то так не очевидно, что почему можно, если локально есть квазиизоморфизмы с какими-то объектами, то почему они
Могут так смотреть, да.
склеятся в один большой морфизм производной категории?
Сейчас нет, но я помню, что здесь важно, что мы не можем сделать исключение для фиг points, но мы можем это сделать для, вот следствие не работает для fig points.
Сейчас,
Оно работает только для строго совершенно.
вот что-то есть в сравнении с перфектом.
Но потенциально есть, да.
А что может быть там? То есть, ну, вот как мы можем получить что-то не строго чисто?
Нет, ну, это должна быть какая-то, для схем, то должна быть какая-то очень такая плохая схема.
Нет, ну да, я понимаю, но вот идея, как мы, то есть, что мы должны там проделать, чтобы вот получить что-то не... То есть у нас же, мы когда это все из x составляем, да? То есть там всякие саманды у x и ну, саманды прямых с x. Казалось бы, это все Вася считает, то, что мы есть perfect, то что-то, что мы локально можем брать. Потому что да, тоже как-то локально можем брать.
Да, ну потому что есть проблема, просто есть теорема, которая гарантирует то, что тыква x совпадает с perfect. Это теорема, что у вас на x должно быть разрешающее свойство. То есть, что да, разрешающее свойство означает, что, грубо говоря, берете там любой когерентный пучок, и он накрывается локально свободно. Ну, не накрывается, а просто есть морфизм уже локально свободно. Вот. И, соответственно, видимо, то, что здесь нужно, то, что вы, наверное, можете взять какой-нибудь там, я не знаю, прямое слагаемое x, и прямое будет непонятно, почему он накрывается локально свободно.
Почему прямое слагаемое x накрывается локально свободно, будет непонятно, мне кажется.
На произвольной схеме, которая, на произвольном операционном пространстве, которое передано локально операционное,
ну, если это сама, то...
не, он накрывается лицом.
Ну да. Да, это как раз не проблема. Ну, наверное, там будет какая-то.
Нет, ну, в общем, я хочу сказать, что это будет верно, все-таки не для всех схем, а для нормальных таких, ну, таких, которые у нас есть приложения, на самом деле.
В принципе, ну, тот пример, который я привел, это, в принципе, и строго чистый элемент. То есть, если у нас у x развивается какой-то плюс, то оба из них строго чистые.
Что такое строго чистые?
Ну, strictly perfect.
Строго совершенно.
Совершенно, да.
Да.
Ну, то есть, для них точно должно быть. Ну,
Они строго совершенно, да.
для них точно должно быть. Да. Почему? Пока не совсем понимаю. В принципе, плюс-минус вот эта теорема тоже у них такой же вопрос, на самом деле, можно задать, наверное. Ну да, типа тот же самый пример, когда я подобного значения. Так. Но упражнение так мне даже интуитивно казалось, как я могу выразиться, там несколько шагов, и поэтому, собственно, следующий.
Ну, поэтому можно подумать, можно через неделю поговорить.
Ну да.
Может, здесь есть какое-то такое простое наблюдение, которое это все спасает.
Да, вот, лучше просто что-то не действительно.
Да, а вы, кстати, спрашивали 2 недели назад там примеры, чтобы были не толстые категории.
Да.
Мне кажется, такие примеры можно строить, как грубо говоря, когда вы смотрите морфизмы схем, да, и смотрите на образы, ну, производного функтора, я все прямой сделал, производные прямые образы. Вот это, ну, такие как бы примеры, они нужны для всех приложений, но и они как бы, ну, априори совершенно не должны быть толстыми.
Правда, что в полбека структурного пучка всегда структурный пучок?
Да.
Ну, это хуй-то.
Ну, это по распределению полбека может
Да. Там же фулбэк это типа тензорное произведение.
А как есть тензорное произведение?
Что
А,
такое
в смысле?
фулбэк? В смысле, фи
Вот
минус
полбэк
один.
это у нас сейчас.
Это у нас тензорное произведение.
сразу утверждение. Потому что это операционное пространство. Это же не просто топологическое пространство.
А.
Обычно, если типа без контрольного произведения, то это он пишет не с оглядочкой, а минус первый. Это прям просто другой функт.
Okay, so there is another kind of notion that I want to introduce. So let me assume, or maybe let me call this as another title. So Tor amplitude. So I want to assume that I have a map from X to Y. So this is a map of rate spaces. And I also want to assume that in this section sometimes I'm going to work with the interval. So by this I mean that this is just a subset of the integers. Well, potentially all this A or B could be infinite, or they also together can be infinite, but in interesting cases it can be finite. So definition. Suppose I have some k in the derived category of its modules. So then, again, definition is three parts. So k has Tor amplitude in the interval relative to given morphism f, if we have the following property, we will look at the homology, so say with the index p, of the tensor product of the given object k, of derived tensor product with the pullback of the f, and this has to be 0 for all p which is not in the interval, not an E, and also for any f which is just a module or y module, so module of y. So that's a Tor amplitude of the complex. Yeah, and also there is notation that I want to introduce right away. So notation for this is quite long, Tor amp, and since this depends on the map f, I also can write f if this is not clear from the context which f I'm using. So this Tor amplitude of the k. Oh, and the definition I can write this as the Tor amplitude of k is contained in the interval I. So that's the notation for this situation. Well, and then you can also do the same definition locally. So k has locally, say, finite. Of course, the interesting case when this is some finite interval. So locally, sorry, maybe before I do this locally, I need to introduce one more thing. Notation, definition. So we say that f, sorry, not f, k has finite Tor dimension. So finite Tor dimension, again relative to f, if it has Tor amplitude in a bounded interval I. Okay, so then for this notion I can introduce the local version. So k has locally finite dimension, again, this is relative to the given morphism F. So if there is an open covering, say ui of the y, such that k restricted to the ui has finite third dimension, or any index I in the covering. Okay, so that's a long definition. So part 2 of the definition. There's a special case, so I can take this morphism F to be just the identity on some ring space X. So I don't want to repeat this, but then we can again introduce the Tor amplitude. Now this will be an absolute notion, doesn't depend on the morphism. Then we introduce Tor dimension.
Можно вопрос? Покрытие УИ, оно и цель не клика? К на X же?
Сейчас, где у нас живет?
Нет. Can you
Сейчас.
Какого еще все сыграть тогда? Нет, ну,
Сейчас. Исана, да. Да.
И мы просто ограничиваем F на УИ.
Да. Просто заменяем как бы условие на то, что оно локально выполнено. Да, в общем, во второй части хочу сказать, in the second part I just want to say that you can kind of repeat everything, but for the identity morphism you still has the notion of the Tor amplitude, Tor dimension, and you can do this locally. And 3 is another special case of the first definition. We can take in this special case K to be just the structure sheaf on the X. And so then in this case we can introduce the notion of the Tor. Well, we can say that the Tor amplitude in this case relative to the morphism F of the structure sheaf, right? So this is contained in the interval minus t0, right? So this is, by definition, is equivalent to saying that F has Tor dimension less or equal than t. And as a formula, we can write this, that the Tor dimension of F is less or equal than t. Okay, so 2 and 3 are just special cases. Well, you can ask me why this is kind of to the negative t, right? Not from the 0 to the t. Well, because the kind of the derived tensor product, if you want to compute Tors, this Tor by definition is homology, so this derived tensor product, if you want Tor n, you compute cohomology with the index minus n. So this explains this kind of way I start from the minus t to the 0, and not from the 0 to the t. Okay, so that's the definition. Yeah, and also in the part 3 you can also do the same. So you can, well, we can, I don't want to repeat this long definition with choosing open cover. We can talk of locally finite Tor dimension of some morphism.
Yeah, and just for the knowing of it, if we take affine scheme and we take Tor dimension of identity morphism, that will be just a Tor dimension of this loop.
That's true if you kind of already know the definition of the third dimension of the rig.
Yeah.
This is just the short it seems. Okay. So before we prove this, I want to prove actually just two statements and maybe give two other exercises. There are several relatively trivial remarks as usual from the definition. So for example, the first one, so if I have torque amplitude relative to f of some object k that lives in some interval ab, well then of course I can take the shift of this k by some integer I. Oh, and you can see that this now lives in the interval a minus I, b minus I. So that's for any integer I. Okay, so the second simple remark is if I assume that the torque amplitude of the object k so is in some interval with a and b, so then this k is in the derived category with the interval a and b. Right, so meaning that there are no homology outside of this interval. Right, well this is simple because well you can take
Structure shift. Structure
Yeah,
shift.
if you want to compute this homology, right, you can as well just write this as the homology of the object T times the product with the structure shift on Y, which is again the structure shift on X, and the draft as a product doesn't do anything. Which is so this is 0 for any P which is not in the interval A. So that's a simple remark. Yeah, so 3, another quite simple remark. So let K be a complex of flat OX modules concentrated in degrees A and B. So then the torque amplitude of this. So the torque, so there is no morphing here, so the torque amplitude in the absolute sense. In the A. Okay, so 4. Torque amplitude of the complex K lives in the interval 0, 0, if and only if, well, this K is just a like module. Yeah, but maybe this is that's not exactly correct. So I need to assume that I have this assumption for the torque amplitude, and I also assume that the K is actually a module. So this is module over X. So then this is the same as saying that K is flat. Okay, so I think that's all the trivial remarks I want to say. There are others, but they even simple. For example, you can, where is this? Yeah, so you can take the part 3, and you can notice that if you take the say strictly perfect complex, right, that lives in the degrees AB, or lives in the degrees which is in interval AB, then this is clearly has Tor amplitude there. Okay, so most of the proofs here are relatively straightforward, maybe except 2 proofs. So I want to give you several kind of propositions with the proofs left as exercises. For example, this one. So suppose we have a distinguished triangle. So let K K, L, and M be a distinguished triangle. Of course, distinguished triangle in the derived category of X modules. So if K and M, so K and M has Tor amplitude in the interval AB, then the same is true for, K and, K and M, yes, that's right. The same is true for the L. So then Tor amplitude of the middle term is in the same interval. Which is easy, and the proof is really just, well, you take a tensor product with some F derived tensor product and look at the cohomology from the whole exact sequence of cohomology. So really it's just a waste of time to prove this on the whiteboard. So this is a simple observation, and now I have something less simple. So let me assume that the K is some object, and I have some interval, and in this case I want to say this is a finite interval, so this A and B can be infinite, so finite interval in the integers. So then the following 2 conditions are equivalent. So first condition is that the Tor amplitude of the K is in this interval AB. And the second condition is that there is a complex, say E, of flat OX modules with EP equal to 0 for P outside this interval AB, and an isomorphism of the E and the given complex K in the derived category. So this is what the remark number 3, which is the trivial one, but in the other direction, right? So in one direction, so from 2 to 1, this is clear. So really the statement is that you can go in the other direction. Okay, so first of all, since we know that the Tor amplitude is in A and B, we can say that if we look at the cohomology with the index P of this complex K, then this is 0, of course, for all P which are greater than the integer number B. Okay, so then there is a complex consisting of flat Onyx modules with the property that the GP are all equal to 0 for P greater than B. And isomorphism from the G to the K in the derived category of all its modules. Okay. Why there is such a complex?
It proves that any bounded above complex has a flat resolution. So we can truncate K
Yeah.
and then find this resolution.
Yeah, so by the general properties, right, so that we proved we studied with categories, so the flat OX modules form a Snowden class, right, so then for the bounded and of complex, there is kind of this standard procedure that you construct this resolution by induction, and then you get this this kind of flat resolution. We can alter this actually K flat, right, because this is bounded and of complex of flat modules, this is K flat. Okay. So again, we can look at the cohomology. So cohomology is A of the G and the cohomology of the K. And clearly they are all 0 for any P greater than B. So since we have this, we can say that the oh, sorry. No, this is of course true, but what I want is that this is true for any P, for any P less than A. Yes. For any P less than A, this is also, since we have quasi-isomorphism with a trivial cohomology, and then this G is quasi-isomorphic to the truncation at the level A of the G, right? And I want to denote, no, actually that's the object that I want to construct in the proposition, so I want to say that this is by definition E, right? So we want to show, well actually by the construction of this E, since we take this and the what's called good truncation, right? So the only problem is to show this doesn't change objects that we have in the E for the index A plus 1, A plus 2, etc. So the only potential problem with this E is at the level, at the position A, right? So since here we have some proper node. So what we want to show, so we want to show that the EA is flat. That's enough, because in all other positions except the position A, by the construction all the EPs are flat. So it's enough to show this position we also have something flat. Okay. So we can look at the distinguished triangle. So we have distinguished triangle that we constructed many times before. So we have distinguished triangle with the E prime, which is mapped to the E, and then there is EA shifted by minus A. Right, so everything
By E prime means bad truncation. E prime is bad truncation of E. Or what is it? E prime is vector negation of E, yeah?
Yes, yes, yes.
Yeah, okay, so just...
Yeah, so it's kind of you have this complex, right? At the position A, you have something, you don't know what it is yet, but all the other terms are flat modules, so we can look at the complex with the flat modules, right? We call this E prime. You have a canonical map from this complex to the E, and the vectorial is just EA. Yeah, so we have this. Yeah, we can notice that in this distinguished triangle, E prime is 0 outside A plus 1 and B, and has flat components. Okay? So then I want to, or maybe I do this in 2 steps. I want to take a tensor product, so the derived tensor product is some F. So take the derived tensor product is F, so it's a 10-graded factor, so we have distinguished triangles to distinguished triangles. So F in this case is an OX module. So then I have the log-exact sequence of cohomology for this new tensored distinguished triangle. And let me just look at 3 terms in this log-exact sequence. So I have cohomology with the index A minus 1 for the tensor product of the E and F. Then this is mapped to the cohomology with index A minus 1 for the EA shifted by minus A tensor product with F. And finally, then they'll get cohomology with index A of the tensor product of the E prime and F. Okay, so
The last term is 0.
hmm?
The last term is 0.
Well, I want to say that these both terms are 0. So maybe let's start with this one. So why this is 0?
Just because E prime flat and E
Yeah.
prime doesn't have any in A.
Yeah, so E prime is just a finite complex of flat modules, right? So that's a K-flat complex. So this really derived tensor product is just an ordinary tensor product. And if you take an ordinary tensor product, this will be still complex concentrated in degrees A plus 1B. So there is no cohomology at position A.
Sorry, what is F? Just a module?
Yeah, F is just a module. Okay, so this is 0. And why this is 0? It's also 0. Yeah, we assume that the object E has pure amplitude between A and B, right? And this is A minus 1.
That's cool.
Okay. So we only have the middle term, and the middle term we can also simplify a little bit. This is the same thing as the, since we have the shift by the minus A, right? So this is cohomology with index minus 1 of the E.
Isn't it 0 just from long exactness?
Yeah, but I want to simplify this first. So I want to make a conclusion from this. So this will be the derived tensor product with F, right? But this thing is precisely the local Tor 1 for the EA and F, right?
Yes.
So, and this is 0, of course, since this term is 0 and this term is 0. So we can see that the local Tor 1 between EA and any other OX module is 0, so EA is flat. That finishes the proof of this statement. Okay, from this we can derive a simple corollary again. I'm going to leave this as an exercise. So let F, maybe it's immediately clear without even an exercise. So let F be a morphism of ring spaces. Let F be a map of ring spaces. So assume that the K is complex of modules on Y. And assume that the Tor amplitude, which I compute just on Y, of the K, this is in the interval AB. So then, yeah, I think it's clear immediately. So you take the derived pullback of the K, maybe just one formula. So you look at the Tor amplitude on just on the X of the derived pullback of the object K, and this lives in the same interval A and B. I think it's clear. You just take this K, use this statement, previous statement, to replace this by this finite complex of flat. This is K flat, so we can compute this derived factor as underived factor is one, I think the most important one, which shows how this works together. So proposition. So let E be an object in the derived category of OX spaces. So I assume that I have integers as before. Writing this to say that I'm considering finite intervals. So if the Tor amplitude on the X of the object E is in the interval AB, some finite interval, and so then E is permanent. Well, if you take a map of the ring spaces, you assume that you have some object on the Y with a Tor amplitude in this interval. You take it pullback, derived pullback. You look at the Tor amplitude. You take this K, right? Since this has Tor amplitude on the AB, you can, up to quasi-isomorphism, you can replace this by the finite complex of flat modules in this interval, right? So since this is finite complex of flat modules, this is K flat. So when I compute the derived pullback, I can just erase this derived, which only lives in the degrees A and B.
And it's still flat.
Pretty much sure the flat is flat. Is that so?
So if not, then why?
I think the pretty sure the flat is flat. I think my the proofs, never mind, it's just quite complicated. It's something confusing, complex, Lazar's theorem. But I think there is a simple proof. Let me just try to compute the Tor 1 with any other module. Well, but actually, do we really need this? Because the condition we need to check is that, okay, I take this f upper star applied to the k, right? So that's a finite complex. So, yeah, I think I need this because I take the derived as a product,
Yes.
even if I take this with the module, right? But
Yes,
this is derived as a product, you can move it somewhere.
It can go to the left.
Yeah, I think that's probably pullback of flat is flat. No, I think this is something that usually done in the algebraic geometry class, so unfortunately I don't remember the proof. So I said this is another exercise.
But it is true. That the
Yeah, but I understand that's kind of how to prove it for upper rings.
so is it true that the pullback of flat is flat?
Yes. Yes, it is. I think it is true. Well, the reason I have in my head, and I don't really want to kind of use this as the right argument, you can take a flat, you can present this as a directed limit of the free modules, the pullback of the free module.
It's free. It's true.
Yeah.
And it's just pullback commutes with direct limits.
Yes.
It's not commutes with colimits. Not filled direct
Direct
limits.
limits.
Yeah, so, yeah, that's.
Yeah, but definitely there should be a simple proof that without this cover of laser
As you see, you can just look like on locally what you get, like when you pull back, it's just tensor product with a ring, and you can just, I suppose, just.
Yeah, the flatness you can kind of check locally at the stocks, and for the stocks it's clear, right? Because this is just one local ring, you take a tensor product with another local ring, and this is again flat.
Yeah, it's just.
Yeah, so looking at the stocks is probably the best way to do this.
Okay.
Okay, so yeah, so I wanted to prove this proposition, and this kind of combines everything together, right? So pseudo-coherence. So usually this formulated in a little bit unprecise form by saying that being a perfect object on the ring space is the same thing as being pseudo-coherent plus finite Tor amplitude. Right? Because in the other direction it's of course clear, right? If you have a perfect, it has finite Tor amplitude and it's pseudo-coherent for a minus one, but really for any a. So the unprecise statement that I can say is corollary of this that perfect is the same as finite Tor amplitude plus pseudo-coherence. But this is kind of more precise version. It's enough to consider pseudo-coherence at a minus one. Okay, so let's do this. Again, so working locally, we assume that there is K strictly perfect in X and A minus one isomorphism. Let me call this alpha from the K to the E. Right, so this is what I get locally from the condition this is pseudo-coherent. Well, since I know that I can check pseudo-coherence, so the pseudo-coherence for the K is the same as pseudo-coherence for the truncation of the K, I can say that I'm replacing K by the silly truncation at the a minus 1, okay. So we may assume that Kp is equal to 0 for any p which is less than a minus 1. Okay, and since we also know this E has Tor amplitude to the AB, so without loss of generality, I can also assume that if P is 0 for any P less than A. Okay? Now I have this morphism alpha, and I want to complete this to a distinguished triangle. So complete alpha to a distinguished triangle, but not on the right, but on the left. So the distinguished triangle I want to consider is G, which is mapped to the K. By the map alpha, this is mapped to the E. So that's a distinguished triangle. Okay, so then I have for this distinguished triangle one exact sequence of the cohomology. So what are the cohomology at the position A minus 1? So for the G. Right, so for what's some cohomology, I don't know yet what it is, but what about the cohomology for the complex K, right? Since I can assume that the Kp is equal to 0, right, for the P less than A minus 1. I can write for this cohomology with the number A minus 1 simply as the kernel of the K with the index A minus 1 to the K with the index A, right? By this assumption. Okay. Yeah, and what I'm writing the equality here. So what about the homology of the E at the position A minus 1? Right, it's 0. Right, so, and it's also a homology of the E at the position which I have kind of, that I need to write on the left with the A minus 2, it's also 0, right? Hence I have this isomorphism of the homology. So let me call this, for shortness of the notation, I want to call this homology just C. Okay. So how about the cohomology HP of the complex G? So I claim that actually this is 0, right, for all P, which is not equal to this term that we've just discussed, not equal to the A minus 1. Right? This follows by the fact that we have this finite Tour amplitude and pseudo-coherence. Okay, so if this is the case, well, actually this G is a very simple complex. So we can write the G as simply module C that we obtained before, shifted by the 1 minus A. Right? But that is precisely the same thing as the truncation, good truncation at the on the right at the level A minus 1 of the complex K. So this last equality is by this thing. So if we compare two distinguished triangles, one distinguished triangle is the kind of the canonical one, which we have for any complex. So we have truncation mapped to the K, and then there is truncation. I think I've done this complex when we discuss truncations. So that we always have something like this. And then we can compare this with the distinguished triangle that we have kind of before by the definition of the G. So we see that kind of K is the same in the middle, G is isomorphic to this truncation, right? So comparing this and this, I can make a conclusion that there is a quasi-isomorphism between E and the truncation and the A of the K.
That's all.
Hmm?
That's all, yeah.
No, not really. Well, how do you know? How do you know that this is perfect?
It's locally isomorphic to S perfect.
Oh, it has a truncation again. So truncations is something that ruins this conclusion.
That's true.
So what we want to show, finally the last goal, is that I'm going to call this L again for shortness. I don't want to keep this truncation. So L is by definition this truncation at the A of the complex K. So I want to show that this is strictly perfect. Okay, so again, I think I can say that it is enough, as in the previous proof, to show that L with the index A is a direct summand of a finite free OX module. Right? Because for all other terms except LA, everything is clear.
Why is it enough to show that it is the direct summand, not a free OX module?
Because in the definition of, I want to show, I'm working locally, so I want to show this is strictly perfect. In the strictly perfect, by definition, I need to have terms which are direct summands of a finite free OX modules. Okay. So for this, I have two observations. So the first one is, well, which follows more or less from the definition, is that LA is the co-kernel of the Ka minus 1 mapped to the Ka, right? But it means, in particular, that LA is of finite representation. So then I look at then the proof is more or less the same as before. I look at the distinguished triangle, L prime L mapped to the LA shifted by minus A, so all other terms except LA is kind of in this L prime. So that's a distinguished triangle. So then I apply tensor product, so derive tensor product with F to this distinguished triangle, and F is any OX module. So F is module of OX. Again, I look at the corresponding exact sequence of cohomology, just in the three terms, HA minus 1 L tensor product with F. So I'll simplify this immediately. So the middle term will be, as before, H with the index minus 1 LA tensor product with F. And then HA L prime tensor product with F. Okay, so as before, this term is 0, right? Because the L has Tor amplitude in the AB, right? So then this is also 0, right? Because I can write the derived tensor product, or can just erase this derived tensor product, since this is a K-flat object, and it's concentrated in degrees up to A plus 1 to the B, so there is no homology here. So the reasoning is the same as before. So this thing is the Tor 1.
Why L has Tor amplitude? Why the left term vanishes?
So this one.
Yes, because we know only that E has such Tor amplitude, but then we truncate its somewhere. And why we know that L has
No, there is E in this distinguished triangle.
Yes.
We know that the E is quasi-isomorphic to this truncation.
Yes. Oh, yes. And it clearly doesn't depend on quasi-isomorphism.
Yes. Yeah, so in the middle we again get the Tor 1 between LA and NEF, and this is 0. So that's a finite presentation and flat. So hence this is a direct summand of a finite free OX module. That's okay. So yeah, maybe so that's a detailed statement. Maybe I just formulate the special case that you can remember. That's the slogan of this situation. So let me formulate this even a theorem, which is actually just immediately follows from the previous proposition. So E is perfect on all X if and only if E is pseudo-coherent on X and Tor amplitude of E. Well, I'll just write this inverse is finite. Okay, so let's finish this part.
Where we have used that LA is a finite presentation. Where we use that LA is of a finite presentation.
Well, in the commutative algebra, you can expect it to know this, that if you have a module which is, for a module of finite presentation, being flat and being projective is the same.
Yes.
So this is generalization of this situation for any ring space. This is still true. So if we have a module which is a finite presentation which is flat, then this is actually a kind of, if this is also,
So we have proved that it is flat, and so it is a direct summand.
yes. So that's I'm using kind of some general properties of ring spaces. I'm assuming that you know this or you can believe this because you know this for commutative rings. And that's not actually not a trivial statement for if you just have any ring space, you don't assume anything. For example, you don't assume this is locally ring, and you just take any ring space and you say that you have a module which is for finite presentation and which is flat, and this is a direct summand of the OX to the n. That's not a trivial statement. It's you can't just immediately reduce this to the commutative rings. Look at this as an exercise if you don't know this. I think it's simpler if this space is locally ring, simpler if this is a scheme. Okay, and that's the slogan of this situation. That's something that you can remember. Okay, so with this, I want to finish this.
So is it true that LA is projective? Is it true that LA is projective?
Yeah. Projective is like locally free.
What do you mean projective on the?
So it is projective in the sense that it is a direct summand of finite free module.
Yeah, it is locally projective.
Yes.
Yes, this is locally projective. For schemes, I think this is clear because locally you can just work like all the only commutative ring and you know this. For ring space, you need to do something more. Okay, so I want to finish this first section of the chapter 6, and I want to go to the second. So this was kind of some generalities about the ring spaces that we can will need later. Maybe I'll discuss more generalities that actually need for this course. So now I want to again kind of combine all the generalities about the direct categories of quasi-coherent modules. So in this chapter, I want to assume that X is a scheme. This will be, no, not chapter, but in this section. I want to assume that X is a scheme, and I want to use short notation. I'm going to write dx. This is will be by definition the derived category of all X modules with quasi-coherent homology. This QC is supposed to say quasi-coherent, so let me just write this in words. So the derived category of X modules, of complexes of X modules, of course, with quasi-coherent homology. Okay? We need to distinguish notation d of x and d of ox. This is not a standard notation. In many resources, d of x is just this, what I use for d of ox, so you kind of need to be careful.
Well, it's also a main notation D of coherent of X models.
Well, there will be no coherent stuff in this course, so it's not a problem. So mostly we're going to work with quasi-coherent. Okay. So the first thing I need to show is just a statement about the abelian case. Is I want to show that the abelian category of quasi-coherent shifts on any scheme is a Grothendieck category. And to do this, I need to create some preliminary work. So maybe let me kind of write this as some subtitle. So QO of X, which is the abelian category of quasi-coherent OX modules, is a Grothendieck category. So, first we have a definition, quite general, again for ring spaces, so let X OX be a ring space. So gamma is an infinite cardinal so then we call sheaf F of the OX is gamma generated if there is an open covering so let's call this UI of X. So there is an open covering such that so F restricted to the UI is generated by some sections, so let me call this Ri, so that's a set of sections. So that's a subset inside F of the UI. And cardinality of the Ri is less or equal than gamma for any I. Okay, so first I have a quite simple lemma, which more tautological. So isomorphism classes. So isomorphism classes of gamma generated OX modules form a set. Well, the proof is, and you just look at everything and that kind of controls this definition of gamma generated and check that everything that you have in the definition form a set. Well, for example, there is a set of coverings. So these are coverings without repetitions. So there's a set of coverings. So if we have a covering, so let X be a union over I of the UI. So that's a covering, and Fi is a module over OUI. So then there is a set of isomorphism classes of OX modules F such that F restricted to UI is isomorphic to the Fi. Right? And if on each UI we fix this Fi, right? So the isomorphism classes form a set, well, because kind of you know this locally and you want to glue them together. But the gluing data again form a set. So that's a set. And finally, we need to show that these Fi's for each index I also form a set. Right? But this is true because because every Fi, since this is gamma generated, right, so we can look at the direct sum, say, over gamma of the OX to the Fi, right? So there is only a set of such quotients. So there is a set quotients of direct sum of gamma OX. So together, combining all this data, we can say that they form a set. Well, using the argument, something like you take a union over a set of sets, and this is still a set. Okay, so that's kind of the silly part of the construction. Now we have the main important technical part, the lemma. So the statement that for any scheme the category quasi-coherent sheaves form a Grothendieck category, this is usually attributed to the Gabor, but it was never kind of published anywhere. So there are papers that kind of use this argument and attribute this argument to the Gabor, but there is no paper of Gabor about this. So the lemma is the following. So let X be a scheme. So then there is a cardinal gamma such that any quasi-coherent OX module is the direct limit of its quasi-coherent gamma generated submodules. Okay, so for the proof I choose an affine open covering. So choose affine open covering. So X is the union of the UI or some index I. And so of X, and also choose an open affine covering for the intersections. So take UI, intersect with UJ, and write this as the union over some K of UI that's another open affine covering for the intersections, for the intersection UI and UJ. So fixed annotation. So UI will be spec of the AI, right? It's open affine covering, so there's corresponding ring. And also UIJK, this will be the spec of the AIJK. So gamma is the infinite cardinal, which is at least maximum of the. Oh, I need to give names for the indices. So in this open affine covering, I'm going to say that the index little a is in this little I is in this set I, and for this and the intersection of two open subsets, I'm going to say that this K is in the I with the indices I and J. So this is maximum of the cardinality of the set I and the cardinality of all the sets I, J. So this is how we choose this cardinal that we have in this statement. So for F, which is now a quasi-coherent X module, we set Mi to be F, which I compute on the UI. So this is value of the sheaf of this open set. And the same for the Mijk. This is F, which I apply to the Uijk. So that clearly, since I start with the sheaf, I have the following identity. If I take a tensor product of the Mi over AI with the Aijk, so it kind of just restrict the sheaf to an open subset, then I'll get Mijk, and if I do this in the other order, so Mj, not the other order, not for the I but for the J, I'll get the same answer. Because this is a sheaf. Okay. By the axiom of choice, there is the following mapping. So there is a map that takes I, J, K, and M, and maps this to the S depending on the I, J, K, and M. So I'm going to explain this notation. So here, of course, I and J are just two indices, two elements in the set OHI. K is just an index in the Ij. And M is an element in the module Mi. So then S, depending on the I, J, K, and M, is a finite set. So it's a finite set such that I write tensor product of the M with 1, and I know that by the previous observation.
Shouldn't M be in Mijk?
No, in Mi. Right? I want to start this M in the Mi, right? So I take a simple tensor here, which is Mi tensor 1, and I know that I can kind of pick up rewrite this as a sum tensor here, and this tensor will be a sum over finite set. So this will be sum over M prime, which lives exactly in the set S, I, J, K, M. M prime tensor of sum AM. So this is of course some. So this M prime. So I need to say that, for example, A M M prime.
What do you mean by M prime lies in such set?
MG.
Yeah, but
M prime is an MJ.
what is SIJKM?
Well, that's some element, right, that lives in particular in this tensor product.
Mm-hmm.
And any tensor can be written as a finite sum of this form.
Mm-hmm.
So I'm just doing this, and I'm just fixing one way to kind of do this.
So there is a map from set that consists of IJKM such that IJK and M is set 0, and it gives us a finite set of elements of MG.
Yes.
Uh-huh.
So the finite set of elements in the MJ. Yes.
How it follows from axiom of choice.
Well, there are many ways to write this. You can kind of choose one way, right? For this data, for this kind of for topole of the data, you need to choose one such sum. Or potentially there are infinitely many such sums.
Okay.
Yeah. So I just wanted to write where this AM prime lives. This is in the ring AIJK. So, and also I want to, for the special case where everything is trivial, so for I equal to the J, we fix our choice and say that the S of the I, K, and M, this is by definition just M. Right? Because in this case, if I is equal to J, Mi is the same as Mj, so this makes sense. Okay, now suppose I have the following. Suppose I have the whole family, so this S, and curly S, this is supposed to represent the family, so this is family of Si, where I is in the index, of index in the set large I. So Si with the index is a subset in the module Mi.
Is it the same I that we already used?
Yes,
Uh-huh.
yes. So the cardinality of the Si is less or equal than gamma. Then we kind of have this procedure. We set S curly S prime to be another set of the same form. So this is family of Si. I is running over the set large I. And S, yeah, so this is supposed to be primed here. So this is Si prime. So Si with the prime is defined as the union of all the I, K, and M of the sets S, I, J, K, M. Okay, so we need to notice two things. So notice, so construction about this set. Well, first of all, that the Si is contained in the Si prime. And the second observation is that if I look at the cardinality of the S prime I, so this is still bounded by the cardinality of the gamma, right? Because we take the union, right, and the union over the set which is bounded by this cardinality, and each set in the unit is just a finite set, and gamma has infinite cardinality, okay, infinite cardinal.
Why Si lies in Si prime?
Oh. This is just kind of follows from the definition, right? Well, because we have this special case, wait, this one, right? When I is equal to J. So in particular, when you do this, you have a situation where I is equal to J.
Yeah, yeah, repeat why SI prime has coordinates as well as gamma?
Well, because we have this, which is defined as the union of the sets, right? And we take a union over a set which has cardinality bounded by gamma, and this is a finite set.
Yeah, of course.
Okay, so we use this procedure to produce this infinite sequence. So I have currently S with 0, this is just the S by definition. So then currently S with 1, and this is defined to be the currently S prime, which is given by that construction. Right, so then I continue doing this and say that the currently S with the number, say, n plus 1 is defined to be I take the currently S with the number n, and I need to write this in parentheses. Right, so this is this thing with the prime, etc. And finally, currently S and to the infinity is defined as the union of all this Sn. So why we need this definition? Well, the explanation why we kind of use this strange construction is the following: that if when we do this strange construction, we have the following for m, which is in the S currently S infinity with the index I. Its image in the Mijk can be written as a finite sum, so sum m prime tensor am, so where a prime is in the S currently S. No, this is sorry. In my notation, this is not currently S. This is just S. So S, and this is S. Right, because currently S is the family, and S is just for particular inputs. Okay. So if I now define M with the index I to be just a submodule generated by the Si to the infinity over Ai, so that's a submodule inside Mi. Then for this, I can write the tensor product of the Ni over Ai with the Aijk is the same as the Nj tensor product with the Aijk. So, since they coincide on the intersections, we can conclude that we construct the G, a subsheaf inside F. So, with the property that the G on the UI is Ni, and G is gamma generated. So then we look at the family GT. So the set is the set of all gamma generated quasi adherent subsheaves. Well, first of all, we can notice that so is gamma generated submodule or subsheaf. right? Well, this is because we can, if you look at the sum of these two sub-objects, this is can be covered by the direct sum, and the direct sum is gamma generated if each sum is gamma generated. So finally, I want to say that when you take the colimit of the gt over t, then this colimit is f, and hence this is the proof. Start with any given family of local sections Si. Right? So you have this open covering for each in this I. You can choose the local section label Si. Right? And then you have this kind of constructions like this. You can start with a curly S such that this Si, right, so this subset inside Mi, choose any Si that contains this local section. And then do this procedure. And then you construct a submodule, right, such that for a given local family of local sections of F, you constructed the gamma-generated submodule that contains all these local sections. And that's true for any set of local sections. That's the colimit. And the colimit in this case has like a huge union, right? So everything is in this huge union.
What is GT?
It is just a parameter. This is the set of all gamma-generated quasi-coherent submodules.
So we define G without any parameter or
Yeah. Yes. So kind of this argument stops here, right? So I can start with any such family S, and I can construct a submodule G of F. Yes.
So you need to replace infinity again. Then we get if we replace infinity in an I by T, then I get GT.
No. So you kind of pause here for the logic of the exposition, right? And then you consider, well, kind of from this procedure, you see that you kind of have a lot of gamma-generated quasi-coherent subshapes, right? Which you can produce by doing this. Start here and do this, right?
Yes.
And then you just denote all the set of all gamma-generated quasi-coherent matrix. So the T is this set
Yes.
of sub-objects.
Yes.
Yeah, and then we can kind of check that this set is directed, so it's closed under. Well, you can take the direct sum, right? And hence this is directed, so it's a directed set. And then I explain that if you take a colimit of this directed set, you get F, right? Because intuitively think about this colimit as a union, and everything is kind of in this union.